Hello everyone, I'm Yiyuan from Peking University, and I'm happy to share our work about temporal resource typing, which proposes a type-based solution for verifying liveness of resource usage. And this is in joint work with Taro Sekiyama from National Institute of Informatics. So first, let me introduce what resources are and what we mean by resource usage verification problem. So resources, they are different from other values in programs in that their states can evolve. So the valid operations that you can invoke on a resource can change. Examples such as files, logs, heap memory. So when you have a newly allocated heap memory, it is uninitialized, so you cannot read from it. And if it is deallocated, you can no longer access it. So the valid operations changes. We can specify this kind of usage protocols using we call temporal specifications to prescribe the usage traces. For example, the file usage here says that you should open the file first before it is read or write finitely many times, and eventually it must close. So we are specifying the full traces here. In this specification, we require the files to be eventually closed. And the log specification here says that acquire and release must come in pairs, and this usage pattern can repeat arbitrarily many times, including infinitely. So given these temporal specifications for each allocated resource, a program then is resource correct if during every execution, every allocated resource has a full usage trace, respects its assigned temporal specification. And now I want to show you some examples. So this is our first example, which is an infinitely running loop manipulating files. So in each of the recursive call, a file is created and opened, and its content is read, and then after some processing code, you close the file and continue with the next loop. So you can see this program first, it runs infinitely, which is typical of server programs or interactive applications. And second, every allocated file has a usage trace, which is simply open, read, close, satisfying the temporal specification for files. So this is a usage correct program. And before presenting other invalid examples, I want first introduce the notion of safety and liveness because it appears in our title. So colloquially, we usually say safety is all about preventing bad things happen or nothing bad ever happens. And liveness is about eventually something good will happen. So consequently, there are two kinds of violations when we program with resources. The first kind of violation is that at some point, you invoke an invalid operation leading to a bad state, or more technically, you produce an irrecoverable bad prefix with respect to the file usage specification. And here, if you open the file and close it twice, it is a safety violation. And liveness violations are about so for example, take the file specification as an example. We have a desired event to be invoked, which is the close operation. So here I'm showing a usage that after opening the file, it is read infinitely. So it doesn't satisfy the desired closing operation. So in general, as you can see, safety can be detected by checking prefixes of usage only, but liveness, it cannot. For liveness, we have to reason about the full traces, especially when infinite executions can appear. This is more difficult. So after discussing these two kinds of violations, here's a simple safety violating one. So the same example program, but with close, move up. So you open the program and then close it immediately. But then if you want to read at this point, this is a safety violation, which leads to a bad state. So this is resource usage incorrect. And this infinitely running example here allocates a file at line 6 and then goes into an infinite loop. This loop reads the file in each recursion and continues infinitely. So it produces the trace we have just described, which is open and then read infinitely. Although, as we just say, so this usage trace is a safe trace because every prefix is good in the sense that you can just close in the next step to make it a valid usage. But actually, this desired close event is missing for the full trace. So this is a liveness violation. So now I hope before going to the motivation part, I hope that now you have a good feeling about what resource usage is and what we care about resource usage verification problem. And especially you've seen that for liveness, it is more difficult to verify than safety because it requires reasoning about full traces. So now let me motivate our specific interest in enforcing liveness of resource usage using types. So now let me first show you the landscape about type-based solutions for resource usage verification. So overall, I think in current literature, type-based approaches mostly focus on safety, but not liveness. So for these type systems, they usually, first, they apply invariant-based reasoning to prove type and resource safety. And second, they usually apply substructural typing techniques, such as linear typing, ordered typing, or ownership types, using all these substructural typing techniques for strong update of resources states. So representative works here include type state systems and resource usage analysis and others. And so for liveness, we think there are few type systems for liveness of resource usage. And as explained earlier, I think part of the reason is that it requires reasoning about the full trace in infinite executions. So this is not entailed from type safety alone. So simply put, our goal is just to achieve a type system that enforces liveness of resource usage, which means we need to ensure not just valid or safe prefixes, but also valid full traces. So I'm repeating this phrase multiple times, I just realized. Okay, so our contributions are listed below. So first, we formally described what we mean by resource usage correctness. And I hope by giving these examples, you already have a good feeling about what we care about. And the second and the third bullet point is about our typing technique. And the fourth bullet point is about our proof technique, which requires a logical relation to capture the divergence happens when divergence happens. So today's talk will focus on the second bullet point, which I think is our main novelty, which is a resettable timer mechanism for ensuring liveness of resource usage. Okay, so to understand current work and our work better, let's first start by modeling temporal specifications as transition systems. So let's consider again this file example. We want this transition system to accept exactly the valid usage traces of files. So it specifies that a file starts from the initial state as init, and then you can open it to go to the second state, open state, and optionally you can read and write finitely many times, and finally you should call the close operation to go into the double-circled accepting state, the closed state. So in this way, by modeling temporal specification as a transition system, a resource usage can be represented as transitions between the sequence of visited states. So, let's revisit the definition of safety and liveness again. So in this transition system view, safety is it is a local requirement that you should always take a valid transition in each state. On the other hand, liveness is a more global requirement, which requires the visited states eventually reach some accepting state. So here is a valid usage. So you open, read, close. So each of the transition is valid, so it is safe. And eventually, you also goes into an accepting state. So this is a valid usage, satisfying both safety and liveness. And to understand current research on type-based resource usage verification, they usually follow these steps. The first step is that since we have this transition view of resource usage specifications, we can encode in the types of resources these resource usage states. So for example, let's consider type state systems. So the resource types carry directly the state of the resource. So a just open file has this file type with the type state of opened. And the second step is that for these resource operations, you need to update the type state in these types. So for an open event, it corresponds to the transition from init to opened. And lastly, for sound strong update in the presence of aliasing, usually some substructural typing technique is applied. But that's mostly orthogonal to our research because we focus on liveness reasoning instead of supporting aliasing. So here, for simplicity, in this work, we just apply uniqueness typing, and you will not see any problem about aliasing in the rest of the talk. Okay, so in this way, let's see how our type system catches safety violations. And in this program, a file is created, same as before, and it is opened. So it goes from the initial state to the open state, and then it is closed, goes into the closed state. And at this stage, at this point, if you invoke the read operation, it is not it is rejected by the type system because the expected type is in the open state, but what we got is in closed state. So we correctly capture this safety violation. However, using this same infinite read example, we can see that liveness violation is not captured using this basic type system. So the file is opened and then goes into an infinite loop of read. So it stays in the open state forever and making self loops. So this usage is safe, but it violates liveness because the desired state close is never reached. So what should we do with this to catch this kind of liveness violations? What's the root cause of this liveness violation? So our observation is that the root of liveness violation is a lack of progressivity. So by progressivity, we mean that resources should reach the desired states, or in the transition system view, the accepting states, within bounded time steps. So in our infinite read example, although the execution continues infinitely by recursion, the resource, its usage state, is stuck in the second state, open state, and never make progress towards the desired state, the closed state. So conversely, let's consider a valid example with a progressive usage of files. So this example is slightly more complex. So this recursive function takes in two files, and the first one is assumed to be at open state, and the second one is a initialized file. And in line 2, we close the first file and open the second file, and we create a new file. Then we give the resource y as the first argument of the recursive call and pass the newly created z file as the second argument. So by applying some invariant-based reasoning, we can see that each allocated resource has this usage pattern of creation and then opened and then closed. And they are this usage pattern happens within 2 recursive calls. So, as demonstrated by the previous 2 examples, one invalid, one valid, we see that our core challenge is to ensure progressivity of resources using types. So our solution is to add a timer to the resource types, and its general form is of resource and has a subscript of its temporal specification and a superscript of its current timer. So when resources are created using the new construct, they are assigned a temporal specification as well as an initial timer. And our intuition for these timers is that they bound the number of recursive calls that a resource can be passed through. So this is manifested in our typing rule for recursive functions, which is a bit simplified version in the first order setting. So as you can see from the typing rule, when argument x is passed to the recursive function call, before evaluating the function body e, we will decrease all of the resource timers inside the argument. So the countdown operation is defined here. So it will structurally go inside the types to decrease all of the resources timers. And if the timer reaches 0 before if the timer reaches 0 before it goes into a desired state, then our type system will reject the program. Otherwise, if every resource reaches the desired state within a bounded number of recursive calls, this satisfies progressivity and hence Liveness requirements. So this is our commented version or well-typed version of ill-typed version of our previous Liveness violating example. Because no matter what initial timer you give to this file, it is not enough because infinite recursive chain happens. Therefore, the program must be rejected. And similarly, this is the valid example. And we have a usage pattern that each resource goes into the desired state within 2 recursive calls. So here I'm showing the evolution of the timers and the file usage states. So you can see when each recursive function application happens, the timer is decreased. And when each effectful operation is invoked, the state is updated. And finally, it goes into the closed state and ensure that the timers are always non-negative. So it looks good for finite usage, but how about valid infinite usage? So here's an example. We are programming with a single lock here. So we newly allocated a lock and goes into an infinite loop, which acquire and release this lock in pairs. And you can see, same as the previous violating example, no matter what initial timer we give to this lock, it is not enough. So the problem is that we need a way to reset the timers. So this is exactly what we do. We add a ghost construct reset to the language. And it allows resetting the timer of a resource whenever the resource is currently in a desired state. So this way, valid infinite usage pattern can continue infinitely by resetting the timer each time it is currently in a desired state. So this is the same example, lock example as in the previous page, but I added the reset at line 5, so it goes smoothly. So here is something about the actual representation of temporal specifications in our formalization. So each temporal specification, as you see, resources can be used in with in a finite usage or using it infinitely. So we have two components. The left one is a set of finite traces prescribing the valid finite usage of a resource. And the second one prescribes the valid infinite usage patterns of the resource. And the infinite specifications is a finite set of what we call lassos. So it is making an analogy similar to the automata theory. So each lasso has an initial component S1 and a repeating component S2, and it prescribes a valid infinite usage pattern by producing some trace in the initial part and then repeating by producing some trace in the repeating part. So this is a general representation that incorporates both omega regular expressions or omega context-free grammars. And a resource is considered to be in the accepting state or desired state if its finite specification is satisfied or it finishes producing some initial finite trace in a lasso and is ready for the next repeating pattern. So yeah, I think that's all about my talk. And I'm happy to take any questions.
Hi, great talk. I had one question that your system support dependent typing such that it would be possible to pass a open file handle to a recursive function multiple times, but the recursive function is like bounded by a few.
Yeah, thank you. I have a backup slide for that. So as you can see, one of our future work is to support value dependency in timers. So when you have a recursive call that is not bounded by a concrete natural number, you have to use some kind of value dependency to support, to type check the program. So here is some example that we think could be type checked if we have value dependency, because here the round robin scheduler, each resource, before it is scheduled, it is how long it needs to wait depends on the current length of the active list or the wait list. So it requires value dependency. But yeah, we think that's possible and shouldn't be too hard. And this is left for future work.
I find this quite hard because you said the timer must be above 0.
Yep.
That means that you have to reason about whether values in the programs are above 0.
Yeah. So some kind of constraint solving is required.
Yeah, sure. Thank you.
Thank you.
All right, let's thank the speaker again, unless there's more questions.
Well, I was going to hold myself up because I am the next speaker by asking a question, but I guess I've been told not to. That's true. Yeah, I have the microphone. No one can stop me. Yeah, I guess my question was, it seems like this has some deep connections to measure theory or generally finding bounds in strongly normalizing languages.
Sorry, I didn't hear.
Sorry, you're getting instructions on how microphones? Yes. It looks like this could have some deep connections to measure theory or generally finding terminating arguments for strongly normalizing languages.
Yeah.
Have you explored those connections at all, or does the theory connect, or is it sort of its own thing?
Yeah, I think these two works are connected, but it is different in that we have a separate timer for each resource. So this is required for each resource. It is a local timer. And for for ensuring termination, we assign a measure to each recursive function, which is a global thing for the execution of programs. So I think their techniques might be adaptable to our setting, but we haven't discovered that yet.
Well, I will say that your timer can be their measure. Like you can literally pass a parameter like your timer with resets as a measure. That's a fairly common technique.
I think so. Yeah, now I understand what you mean.
Yep.